Welcome to module number 7a. We discussed MDL, the minimum description length principle, and in MDL we assumed that we know the model class capital C, and now we're going in this series of modules we're going to discuss how to design the model class. And if we know how to design the model class, specifically if within a model class all the models have the same lengths, that tells us how much penalty we're paying in the first part of the two-part code in return for learning. So model complexity for different parametric classes of data quantifies the penalty for learning. So to get into more detail, we need to pause for a moment and realize that maybe we cheated a bit when we discussed MDL because the length of the model C was assumed to be well defined. Now that's correct when the model class capital C is fixed and finite. But first of all, it may not be fixed. It may vary with n. Because for example, if we have a parametric class, we're going to discuss parametric models soon. It may make sense that as n grows, we have more and more quantization bins, quantization levels as a function of n for the parameter. So maybe the model class C, maybe its cardinality should increase with it. So I said model class was assumed to be fixed. It was also assumed to be finite. But what if it's infinite? That raises the question that when it's infinite, all of your probabilities that correspond to the different models in this model class, they must sum up to 1. And because it's infinite, at some point they start becoming very, very small. So it's unclear if that's even defined. But this is actually in principle can be done. And not only can we define an infinitely large model class, yes, it requires care, but you can even do so for a finite n. You can just have a sequence of more and more and more complicated models, infinitely many more and more complicated models. And for finite n, clearly the really complicated models will be, well, not really useful. So you'll typically, for the finite n, the smaller n's, you'll use a simpler model, a much simpler model. But in principle, you could have such a construction. And again, we're going to be discussing parametric models soon. So what we'd like in this module and the next few modules within the general umbrella 7a, 7b, etc., we're looking for a general principle for model complexity. How much does learning cost us in terms of bits? And to do so, we're striving to understand how the model class, its cardinality, grows as a function of n and possibly also the number of parameters. So let's first realize that we've been discussing the minimum description length principle specifically for data compression, primarily for data compression, but this notion of model complexity and MDL, they extend beyond data compression to data science as a whole. And to see this, look at MDL and revisit the module where we discussed different types of terminology for machine learning. And we said that we have features X and outcomes Y. And given X, we'd like a model C that predicts Y well. That's what we'd like MDL to do. And here predicting well means that we want a model C that assigns a high probability to Y. A high probability to Y, given that we know the features X. So to make this concrete, MDL, in the general case of machine learning, it identifies a model C that minimizes the length of C plus the length for the outcomes Y conditioned on the features X and the model C. And whereas earlier we were only conditioning on C, the model, here we're also conditioning on X, the features. That said, in this multiple module 7a, 7b set, we're going to be analyzing data compression. So back to data compression because it's simpler. We don't need to condition on features. Instead of features X and outcomes Y, we only have data. And to keep things simple, we'll denote it by X. So given a model class capital C, we want the best model C that minimizes the length of C plus the length for the data X conditioned on C. So I've highlighted that we're going to be discussing parametric models, so let's do that. We'll begin with a really simple parametric model with a single parameter, then move to two parameters, and you can probably generalize further. First, the single parameter, the simplest case. Let's take xn, which is binary, 0 or 1. Xn will be samples, and they're independent and identically distributed, or IID. That means that if you think of xn as coin tosses, different coin tosses are statistically independent. And moreover, assuming that we toss the same coin again and again, even if it's a biased coin, a 70-30 coin, each of the xn's, the probability for generating it will be the same independent of n. And now that we know that the probabilities for xn being equal to 1 are independent of the n's, we can simply denote them by theta. And similarly, the probability for the other outcome, xn being equal to 0, is 1 minus theta. Now the parameter theta is unknown. We want to estimate it. To do so, we begin by counting the numbers of zeros and ones in our data, and we denote these by n0 and n1 respectively. Next, we compute the empirical probability. Whereas earlier theta was the probability of 1, the true probability, here the empirical probability is the number of ones, n1, divided by the total length of the data, n. And you'll note that n is equal to the sum of n0 plus n1. And these are respectively the counts, the numbers of zeros and ones in our data. Now that we have the empirical probability, we compare it to the model class. And specifically, in many cases, the model class will have quantization bins. We map the empirical probability to the nearest quantization bin. So that's a single parameter. Moving to two parameters, before generating the sample xn, you consider the previous sample xn minus 1. If xn minus 1 is equal to 0, the probability for the next sample xn being equal to 1 is theta 0. Earlier we had theta, now we have theta 0 when the previous sample was 0. And if the previous sample was 1, the probability for the next sample to be 1 will be theta 1. So whereas earlier we had a single parameter theta, we now have two parameters, theta 0 and theta 1, corresponding to the previous sample being 0 or 1. You'll note that xn is no longer IID because depending on whether our previous samples, previous bits were 0 or 1, we could have different probabilities for the next sample or bit. Let's now discuss examples. Example number 1 will involve, in our data, which is a bit vector, long runs of zeros and ones. Take, for example, theta 0 equal 0.1. So after we have a 0, the probability for generating a 1 is 0.1, meaning that the probability for generating a 0 is 1 minus 0.1, which is 0.9. So 10% of the time we flip from 0 to 1, 90% of the time we remain at 0, and if we flip 10% of the time, that means that we flip roughly a tenth of the time. So typically we're going to have runs of 10 zeros in a row. We could have a single 0, we could have 13 zeros, could even have 36, although that'll be unusual. Theta 1 will now be equal to 0.95. So given that we have a 1, we're going to continue having a 1 with probability 0.95, which means that 5% of the time we flip back to the zeros, and 5% means that 1 in 20 times we'll flip back to zeros, or we'll typically have runs of ones of length 20. The second example will have the opposite types of theta parameters. And by having theta 0 large, close to 1, and theta 1 close to 0, we'll be switching all the time. So theta 0 will be 0.9. After we have a 0, we have a high probability, 0.9, of switching to 1. Theta 1 will be 0.1. After having a 1, we have a probability of 0.9 of flipping back to 0. So we flip most of the time from 0 to 1 to 0 to 1 and so on. Occasionally we have 2 zeros or 2 ones in a row. Infrequently we have more than 2. Now note that if theta 0 is equal to theta 1, that takes us back to the single parameter case. And now it's interesting to think about a situation where theta 0 and theta 1 are different, but they're close. For example, point 0.4 and 0.42. And you can contrast this with a single parameter model where the parameter theta is the midpoint, 0.41. And if you'll think about it, you're given data and you're now trying to identify, is it two parameters, 0.4 and 0.42, or is it one parameter, 0.41? And if you'll think about it, and I think this is a great topic for a final project, you'll need a lot of data, large N, to make these decisions correctly. And again, we have here, started with one parameter, went to two parameters. We could have more and more parameters by looking at more aspects of our data. So that'll be it for module 7A, and we'll continue next time.